Hi everyone. So today I'll actually be going through some of the problems from week 4, stacks, queues and decks. Okay, so I'll select some problems here and I'll go through what is the approach to solving them. Okay, so I'll actually choose the more challenging problems so that at least you all know the approach to solving them. Okay, so I just go through the 12 problems. Okay, and roughly what is the technique needed to solve some of them. Okay, so I won't go through problem A because problem A, if you take a look at this problem, is actually just a stack simulation. Okay, so you can just solve this and follow the instructions. Okay, but what we'll go through is actually problem B, which is find my family, which is, I think, is one of the harder problems in this set. Okay, so I'll teach you how to use a stack to solve such problems. Okay, so this problem, right, if you haven't read this problem, it's actually quite straightforward. So let me just explain it directly here. Okay, so the question is asking you that it's telling you that you are given a photograph, okay, and the photograph consists of many people standing in a line, okay, and different people have different heights. Okay, so for example, right, like that. So okay, so maybe I just draw, okay, maybe I just draw one person here. Okay, one person here, someone short. Okay, 2, 1, 3, something like that. Okay, so right, for example, this guy is maybe 160, this guy is 140, 150, 180. Okay, so imagine they're standing in a line, okay, and you're given a photograph. Okay, so what you're trying to do is that you're trying to use some sort of technology to figure out uh if you are able to recognize some people in this photograph. Okay, so the only clue you have, right, is that you know that you are standing in somewhere in the middle, okay, and you have someone to your left, okay, based on this perspective, to the left that is taller than you, and you have someone to the right of you that is taller than both of you. So basically, you want to try to find whether there is such a pattern within this photograph. Okay, that means, right, whether there's a 2-1-3 pattern. So what do I mean by 2-1-3 is that the person who is the shortest among the 3 people is in between, okay, the second tallest person and the tallest person you can find. Okay, so what do I mean by in this question? Okay, so in this photograph, right, there exists a 2-1-3 pattern because of these 3 people. Okay, 160, 150, 180. This is a 2-1-3 pattern. Okay, so your job is to figure out if there exists a 2-1-3 pattern within the photograph. Okay, so the very straightforward technique, right, is just to brute force. Okay, the straightforward technique is to brute force all possibilities. Okay, so what I mean by that, right, is that you literally, right, okay, use some algorithm. Okay, this algorithm is not really very important now because it's not really you won't really learn how to create a permutation or combination in this module. Okay, but you just find all the possible combinations and then you figure out whether this combination is it a 2-1-3 pattern, and you just need to find one 2-1-3 pattern that gives you a yes, okay, a yes, there is a 2-1-3 pattern. Okay, but what is the time complexity of such an algorithm? Okay, you want to find all the possible combinations, right? So for example, if there's n people, how many combinations are there? Is n choose 3, right? Because out of n people, you want to choose 3 people, and then you figure out if there exists a 2-1-3 pattern. Okay, and what is the complexity of n choose 3? Okay, if you know a bit of math, okay, this is a factorial. Okay, it's in the range of an n factorial. Okay, so the complexity is O n factorial, which obviously is too slow. Okay, because n in this case is here. See, n, the constraints is 3 times 10 to the power 5, okay, which is 300k, right? Okay, 300,000. So n factorial definitely is too slow. Remember that in 1 second, okay, you can at most run around 10 to the power 8 operations. Okay, you already have 300k operations, so n factorial is too slow. Okay, so this approach definitely will not work. Now, a second approach, which after much thinking, right, you might figure out, actually there exists a faster way, which is you don't find all possible combinations. Instead, you try to focus on every single person in the photograph being a possible candidate for this one person. Okay, this person one. So what do I mean is that, for example, at the start, I treat this person as person 1, and I say, is it possible? That means, is there anyone to the left of him that is taller than this guy? And is there anyone to the right of him that is taller than both of these guys? In this case, you realize, you check, okay, there's no one to the left, so obviously it doesn't work. Okay, now you try 140. Okay, you try 140. You set him as the person 1. Now you check to the left of him. Is there anyone to the left of him that is taller than him? I mean, there's only one guy, right, to the left of him. So definitely you just need to check this guy. And yeah, he is taller. So this guy will satisfy the 2 position. Correct? Now your job is to find to the right of him. Is there anyone that satisfy the third position. Third position is taller than 2 and 1. That means taller than 160, taller than 140. There is 150, which is not taller than 160, right? So the only possible candidate is 180, which is the person that will satisfy the third position. Okay, so you found a 213 pattern. Okay, of course, another possibility is setting the 150 as 213, where 160 is 2, 150 is 1, and 180 is 3. So what is the time complexity of this solution? Is if you are brute forcing every person, right, to be a possible candidate for the middle person, and then you still need to iterate to the left and to the right of this person, then your complexity will be O(n) square, because, okay, if I need to brute force every person to be a possible one candidate, that is going to be O(n) by itself. And within this each O(n) candidate, I still need to iterate to the left of this candidate and to the right of this candidate to find the 213 pattern. That is going to be another O(n). So you have two for loops of a nested for loop. Okay, a for loop which is O(n) and another for loop inside which is O(n) again. The complexity will be O(n) square for this second method. Okay, that is still too slow because n is 3 times 10 to the power of 5. Okay, I will ignore the 3, so it's just 10 to the power of 5. And n squared will be 10 to the power of 10, which is greater than 10 to the power of 8. Therefore, it will still be a TLE. Okay, which is this approach, I think this is also a more intuitive approach that many people will solve. Okay, but you still cannot solve this within a time limit. So what is the solution to solving this? Okay, so what is the main idea, okay, to find a 213 pattern? The main idea to find a 213 pattern, okay, is that, okay, as you iterate from the left to the right, as you iterate from the left to the right, okay, you know that you will definitely first encounter a possible second candidate first before you encounter a candidate for the first position, and finally you just need to search for a person who is taller than these two possible candidates. So in other words, this will be the final person you search for. And as you go from the left to the right, anybody can fulfill these two spaces, 2 and 1. Correct? Okay, so that is the first insight. The first insight is this guy is going to be the last person you actually figure out. Okay, now as you go from left to the right, what the second insight you realize is that as you iterate from left to right, okay, anybody, okay, can be the first candidate. And how do you be the first? How do you be someone in the first candidate? Is if you are able to find somebody that you have previously looked through and is taller than this person you are currently looking at. So in other words, this middle guy, right, okay, is what you're actually looking at currently. And you just need to check to the left of you, or the people you have seen so far, is there anyone who is taller than you? Okay, so that is the second insight. Second insight is this. In other words, you need some data structure to help you store all the people that you have previously seen. Okay, you have previously seen. Okay, the third insight is that you want to keep, okay, this guy as short as possible. Okay, why do you want to keep this guy as short as possible, this second candidate? Is because you want to find the third candidate. And the chances of you finding somebody who is taller than both of you is higher if the guy and the second candidate is as short as possible. Okay, notice that this is position 1, this is position 2. And in order for 3 to be taller than 2 and 1, you just need to check 3 with 2, because 2 is already greater than 1. 2 is taller than 1. So what you need to do is that you need to store some sort of record, okay, that stores what is the shortest possible second candidate you have seen so far. Okay, so that is the third insight. Okay, so that's pretty tricky. Okay, so basically, right, the most important insight is that you want to keep this guy, okay, as short as possible, so that as you move on from the left to the right, the person that you're looking at very likely will be taller than this second guy. And if you find someone who is indeed taller than this second guy, then you definitely have a 2-1-3 pattern. Okay, so now what is the algorithm? Okay, so the algorithm, right, is that it relies on the important information, which is that since we want the second person to be as short as possible, okay, we do not want people who are too tall to be inside. Okay, that's because, right, if you had already, so for example, let's say, right, the current record, okay, this record refers to the shortest possible person for this second candidate that I've seen so far. So for example, the record maybe is 180 meters, okay, which is quite tall, right? Okay, then suddenly, as I go from the left to right, I realize there is another record that is maybe now 170 instead. So I will change it to 170, correct? which means the record will only get smaller and smaller. It cannot get higher and higher because I'm trying to make this second guy as short as possible. Okay, so this record will only be smaller and smaller. Okay, and in other words, it means that the previous people that I've seen so far, I do not need to care about anyone that is taller than the current record. Okay, in other words, that if the record now is 165, when I go to the next person, I want to check if this record can be beaten. And basically, what is stored in the people that I've seen so far, okay, you should not be storing people who are taller than 165 because they will definitely not be the correct answer. They will definitely not make a record smaller. Okay, so that is the main idea. Okay, the idea is that whoever you have seen so far, you want to make sure that you keep track of all the people inside the people you have seen so far, and they are not too tall. Basically, they are not taller than the current record you're looking at. Okay, so a very handy data structure to use here is actually a stack. Okay, so why is a stack good? Okay, it's because a stack has this unique property of making something monotonic. Okay, in other words, that every value in a stack is either strictly increasing or strictly decreasing. Okay, so let me show you how this algorithm works. Then you might better appreciate this concept. Okay, yeah. So what you can do is that let's take a look at an example. Okay, that's given in the question. So let's take a look at a more challenging example. Okay, this example is pretty good. Okay, so last example, 170 okay, so let me just write it out. 170, 230, okay, 320, 180, 250, and 210. Okay, so firstly, let's try to figure out whether there's a 213 pattern using our using just by looking at it. Okay, so you will notice that there is a 213 pattern, right? So where is the 213 pattern? It's actually here. 230 can be here 2. This can be 1. Okay, and this can be 3. Right? So this is a 213 pattern. Okay, but of course you do not know that this is a 213 pattern when you're solving this problem. So how do I use a stack to solve it? So let me show you. Okay, so now I will draw a stack out. Okay, and I'll go through the algorithm one by one. Okay, so remember we have a record that stores so what does this record store? It stores the shortest possible second candidate. Okay, in other words, since we want this record to be the smallest possible, we start off with a large number. So I can start off with infinity. Okay, so now what I'm going to do is that, okay, I will go from the left to the right and I will go through every single person one by one. Okay, so the first person, 170. Okay, so 170, I will put him into the stack. Okay, it doesn't really matter because this is the first person. So obviously, there's nothing interesting yet. Okay, now becomes more interesting. Now 230. Okay, so now I have a 230 person. Remember, I'm trying to find a 213 candidate. So this 230 person can be either this 1 or this 3. Right? It can be either 1 or 3. Why can't it be 2? It's because 2, remember, 2 is fulfilled by the people I have looked through before this person. Okay, so 2 is strictly fulfilled by the people that I've looked through previously. Okay, basically 2 is fulfilled by the people in the stack. Okay, remember the stack is what I'm looking at, what I looked at previously. Okay, so now this 230 guy, now I need to ask myself, can this 230 guy fulfill candidate 1? So what does it mean by fulfilling candidate 1? It means that there is someone in the stack that is taller than this 230 guy. Is there a problem here? Yes, there is, because there's only one person previously that I've seen before, and this guy 170 is shorter than me, 230. So obviously this cannot be a 2-1 pattern because 170 is less than 230. So if it cannot fulfill, okay, doesn't matter. I will also need to check whether can it fulfill this position 3. Now, obviously it cannot fulfill position 3. So why can't it fulfill position 3? It's because the record now is infinity. So remember, what does a record store again? Record stores the smallest possible value of person 2. So if record is infinity, I just need to check whether 230 is larger than the record, because in order to fulfill this third candidate. But the record is infinity, so 230 obviously is smaller than infinity. So therefore 230 cannot fulfill the third candidate as well. Therefore, I will put 230 in the stack like that. So let me repeat again. What does the stack contain? The stack contains all the people I've seen previously up to this point. Okay, so this is the point now. Okay, this is the point, and the stack consists of 170, 230. Now I will go to the next value, 320. Okay, this is where things start getting interesting. Okay, not really actually. Okay, still the same thing. Okay, 320. Now I need to ask myself, okay, can it fulfill the first this position 1? So how do I know if it can fulfill position 1? Is there must be a position 2 that I had seen previously. So I check the top of the stack. The value is 230. Can 230 fulfill the 2 position? No, right? Because 320 is taller than 230. So obviously 230 and 320 cannot be a 2-1 pattern. Okay, so this definitely will not work. Now I will check, can it fulfill the third position? How does it fulfill the third position? Is I check the record. Now, 320 is smaller than the record, so it cannot fulfill the third position as well. Therefore, I need to put 320 inside the stack. Okay, now things get more interesting. Okay, now 180. Okay, 180 is very interesting really. Okay, so now this is 180. Now the question is 180. Remember, we always ask ourselves the two questions. Can it fulfill position 1? Okay, basically, in order to fulfill position 1, there must be somebody in the stack previously that has fulfilled position 2. Okay, so let's check the top of the stack. So now let's check the top of the stack. 320, 320 is larger than 180, correct? Which means that 320 and 180 can be a 2-1 pairing. Okay, so what do I do when it's a 2-1 pairing? I will pop it out of the stack. This ensures that this algorithm is ON. So you have to pop out from the stack because so why do I need to pop out of the stack? It's because a stack is meant for you to figure out whether a solution exists. And if 320 is a possible candidate, I remove it from the stack so that it does not get considered anymore. Okay? The reason why a stack is ON is because you do not reconsider solutions that are already possible. Okay, so therefore I remove 320 from the stack. And I tell myself 320 is a possible candidate for position 2. And I will update the record to be 320. Okay, remember the record, okay, I repeat again, the record consists of the height of the smallest possible height of the person as a second candidate. Okay, so the record is now 320. Okay, wait, let me check whether I'm recording. I realize I haven't checked it. Okay, yes, it's pretty long. Okay, so now record 320. Okay, so pretty good, right? Okay, but you realize that I can still do better because notice that the top of the stack is now 230, right? And 230 is also taller than 180 now, which means I can also pop it out from the stack because 230 and 180 can be a 2-1 pairing as well. And I'll update the record to 230. Now I check 180 with the top of the stack 170, but 170 is shorter than 180, which means this cannot be a 2-1 pairing. And I'm done with this algorithm. Now, last but not least, do not forget, okay, to put 180 into the stack. Okay, you cannot forget after you go through the algorithm, you have to put the current value into the stack because 180 can be a potential second candidate. Remember, now we are looking at 230 being the second candidate, 180 being the first candidate. But don't forget that later on, when you see an even smaller number, then 180 can be the second candidate instead. So you cannot neglect this 180. So you have to put it back into the stack. So I put it back into the stack, and now the stack has two values, 170 and 180. Now this is what I mean by monotonic. Okay, do you notice that the values in the stack are strictly increasing all the time? So in other words, notice that the stack at first contains 170, 230, and 320. But when I see 180, I remove 320 and I remove 230 and I put 180 in. And the stack retains its monotonic property. So why is a monotonic property ensures that this algorithm is ON? It's because you just need to check the top of the stack. Once you hit a value that is smaller than what you're looking at, you can stop iterating through the stack. Therefore, this ensures that you do not need to go through a linear path each time. You just need to check the top of the stack. If it is smaller, then you just stop because you know that the values later on in the stack are definitely going to be even smaller. So they cannot be possible candidates. That is why a stack's monotonic property ensures an algorithm is ON. Okay, therefore I put 180 in. Okay, now let's go on to the next value. Okay, 250. 250. So now I ask myself, can 250 be a potential 1 candidate? So I check the top of the stack. The top of the stack is 180, right? 180 is less than 250, so obviously it cannot be a 2-1 candidate. Therefore, I don't need to check for 170 anymore because the top value is already smaller than me. So definitely when I go down the stack, it will be smaller and smaller. Therefore, I don't need to check. I don't need to go through every element. I just need to check the top element. Okay, so it cannot be a 1 candidate. Now I ask myself, can 250 be a third candidate? Yes, it can be, right? Because the record now is 230. And remember, the record stores the smallest possible height of the second candidate. and 250 is taller than 230. Therefore, 250 can be a possible third candidate, and then I can just terminate my algorithm and say, yes, there is a 213 pattern inside this sequence. Okay, so this problem it can be a bit challenging if it's the first time you use a stack to solve a monotonic a question that requires a monotonic property. Okay, so stack problems can be usually very difficult. Okay, if it's the first time you see it. So yeah, so let me just go through this algorithm. Okay, this algorithm is not very straightforward. Okay, but with some practice, you will actually know how to solve this. Okay, so if you want even more practice, I recommend you uh, now you change the problem. Instead of 213 pattern, can you solve, okay, given a sequence, find a 312 pattern. Okay, it is very similar, okay, but there are some very big differences. So trying to figure out whether you can visualize this. Okay, it's actually once you understand this 213 pattern, 312 is actually quite straightforward. Okay, so this is how you use a stack to solve this problem. Okay, it's a pretty challenging problem. Okay, but it's good to know. Okay, so that's all for this problem.